Hello everyone, welcome to the session today. We're going to be looking at the calculation of wind pressures to SANS 10160 Part 3, the South African wind loading code. However, the SANS code is based upon the Euro code, so you'll find quite significant similarities between this and many other codes, or especially those based upon the Euro code. And we're going to look at the procedures to look at a general wind calculation to get a pressure that acts in the area of your building. And then in the next sessions, we'll look at how to apply that pressure to your building, to the specific geometry. Because depending on the shape of your building, with the roof and the sides, the wind pressures immediately around it will change. But we'll look at now how do we calculate, well, how do we take into account where is your building in a country, the altitude, pressures, and all those sorts of things. We're going to start by looking at the procedure to be followed when getting a wind pressure or a wind load on a building. And see, here you'll see a summary of the calculation procedure, which will help you. If you first go through this, and then we'll follow through each step after it. First, we need the fundamental wind speed. What is the wind anywhere in whatever district or municipality in the country we're at? What is the basic, well, what is the speed there? And then we adjust the wind speed to account for certain parameters. Then we need to know, all right, my building, my farmhouse, my multi-story skyscraper is surrounded by buildings or vegetation or mountains or whatever it is. How does that affect it? And then once I've got my terrain category, what is the reference height to know what height to get the wind pressures at? Consider topography. Well, this is where you really account for sort of mountain shape in general, the sort of slopes of the land, where terrain category is, for instance, if you're next to the sea or in the middle of a farm, etc. Then we have a look at our roughness. Once we've got our topography, we get a peak wind speed now. Once we have a peak wind speed, then we can go on to a peak wind pressure. And that is then what we use a lot to be applied to our building, but we have to modify that by the internal pressure coefficients and the external pressure coefficients, and we'll look at that in one of the future videos. Then once we have those, now we know what the wind pressure is adjusted to suit the shape of our building, and then we can apply it to our building in various different ways to get internal and external forces on our building. And then also there is friction forces. We are not going to cover this in our course. The scope of this course is already sufficient that we just don't have time for it, so we are not going to deal with that in our Structural Design 424 course, but you should know that they exist. Here's the equation for the peak wind speed pressure, which we'll only use later, but I'm just putting it to you right at the start so you can have in your mind the fact that we're trying to get a pressure, and this is a function of the density of air and then the velocity squared. And so now let's get down to getting the velocity for our wind. And so we first need to know where in South Africa are we and find out in which municipality we are in, because for each there is a wind speed, and these are all listed at the side, whether it's 32 to 44 square meters per second. And just remember, we square this value, so there's quite a big jump from 32 to 44. It's the square of these numbers. Now, in terms of our course at Stellenbosch, don't worry about me picking some obscure, unknown location. Either we will give you more well-known towns, Cape Town, Johannesburg, Durban, etc., or alternatively, at the back of your code, at the back of SANS 10160 Part 3, there is an annex with the names of all municipalities if you're trying to look up, where are we in the country. So once we know where in the country we are, we get our basic wind speed. So then the basic wind speed is a probability times by that basic wind speed, VB naught, determined above. Here's VB naught. And this is dependent upon the return period or the indicative design working life. And depending on what you're designing, you're going to end up with different returns period. And this table I'm looking at here comes from SANS 10160 Part 1. the basis for design, table 1. So if you've got a temporary structure, you'll design for the worst wind in 10 years. And this is a very short event. This is a couple of second gust. If you have replaceable structural parts, for example, bearings, agricultural structures, and similar structures with low consequence of failure, you'll have 25. In general, we use 50. If not told otherwise, that's pretty much your standard structural period. So most buildings we design are for a 50-year period. However, if you have building structures designated as essential facilities having post-disaster functions, hospitals, communications, fire rescue centers, having high consequences of failure, or having another reason for extended work life, you then go to 100 years. If you have very special facilities, nuclear facilities, etc., then you will do separate designs. You'll have to go look at specialist literature for those. But here we normally deal with 50 unless you have reason to go either lower, if you're willing to accept some failure once in a while, or higher if it requires post-disaster function or high consequence of failure. So we accommodate this indicative design working life in this rather funny looking equation here, and the probability of failure, hopefully you can see this on your screen. If not, refer to section 2723, and it looks not ideal, but all you end up with is k is a value of 0.2 and n exponent of 0.5, and then you have this value of p, which is the probability of exceedance. And so if, for instance, you're dealing with a 1 in 50 year event, that's a probability of 0.0002. So it's just 1 divided by the return period. And what I would encourage you to do is set it up in your code, return period, P, and then you'll see probability. You can do this Excel just by manually, 1 in 10, 25, 50, 100, etc. And you can then go work out, etc. And then you'll find your probability is 1 at 50 years, and then it'll range up or down depending on the year. But if you've got them pre-calculated, it makes your life easier in the future. So just a hint to have that already done. Once you've now said, all right, I've got a building, I know where in the country it is, and I know what how long it's going to last, I can start accounting for other factors. And so the peak wind speed, given here, is also influenced by the roughness, how rough is the terrain around the area, times a topography or orography factor. And so the orography factor is the easy one, taken as 1 unless specified in 733. Now, in Structural Design 424, we will be using 1. We don't have time to cover all the many different clauses, but there's quite a lot of good guidance in the code, which please use in the future. Don't just blindly accept it as 1 every time. If you have a big mountain next to your building, you may have a problem. And you'll see near our university, there is the Kloof Tunnel, and trucks coming out of the tunnel, crossing a big bridge. There is a mountain that channels the wind down and often blows trucks over. So the surrounding terrain can really influence the wind speed. So be careful of that, especially when you've got a big mountain and sort of unusual topography around your structure. In terms of applying the parameters of a wind profile, so depending on your terrain category, you have different values you are going to insert into equations to get a roughness factor. CR at some height Z shall be determined using the following equation. Now, there is firstly the height that you're looking at, so that is the height on your building. Then you've got Z0 is the height of the reference plane, so that you find from here. So you've got a Z0 value, a ZP is the gradient height, so that you've pulled from table. And now what you then also need to have a look at is that there is a ZC value. This is from the table, but it influences what height, will possibly influences what height you use for design. Because what happens is if you look at this roughness factor, As you get higher and higher above the ground, the wind speeds up more and more. So if, for instance, you're terrain category A and you get higher and higher and higher, this is the altitude above, and you'll see the wind speed increases because you multiply CR, your roughness coefficient, by your wind speed. If you're, for instance, category D, your wind speed is much lower, but also there is the zone at the bottom where if you are below a certain height, you don't want to actually reduce your wind speed anymore. Let's say now I have a little building down here, and it's got some height Z, and I'm going to use that height Z to design for. Depending on where that height is, it's fine. I would design it for terrain category A, B, C, but now when I get to terrain category D, if my little building is below the height at which we don't adjust the wind speed anymore, I would use ZC for design. ZC is this cutoff height where the graph flatlines and goes vertical. And so if your Z is less than your ZC, then you use ZC for design. It's a cutoff because you can understand, for instance, with a rough area, with a terrain category D, you have buildings that start and stop and all sorts of effects. You don't really want to reduce this too low because actually you'll see if you extrapolate this, you'll end up with quite a low wind pressure, and it might be too low, too unconservative. So if your Z is below C, use ZC. Otherwise, you use the height of the building to do your design. So coming back, we would put those values into our equation. So our roughness value would be our Z, which is our height of the building, or ZC if Z is less than ZC. ZG, Z0, Z0, etc. we all take from our tables. Just be careful. If you have an older version of SANS 10160 Part 3, there was a mistake here with the value. Sometimes I think it had ZC instead of Z0. Both of these values here should be Z0, but be careful. Older versions had ZC. It was a typo, and correct it if you've got one of the older versions. I think it's the 2011 version or around there. And all right, so now once we have that, we can get our peak wind speed because we would multiply our roughness factor and the other factors together, and we would get to a peak wind speed. We then get to a peak wind pressure, which we saw earlier, taking that wind speed we've calculated, multiplying it by a density of air. And when you get this result, you'll be in pascals. Normally, as structural engineers, we like pressures in kPa, kilopascals, so you just divide this result by 1,000, but this will give you a result in pascals. And so we've got our air density. We need to know what is our altitude above sea level. And so, for instance, we are at 100 or 200 or 1,000 meters above sea level. You would then go use this. You would interpolate between the values, and to be honest, you can ignore structure height normally. You can see these are not big changes in value. So if you are at 100 meters above sea level, you can use that. I mean, normally your 10 or 20 meter high building is not really going to have a big influence of this. So just you can ignore the height typically and not recalculate this for every single height. You plug that in, you now have a wind pressure. In the next session, we'll go on to how to apply that to a specific building. But when we come to look at the building, just in terms of the geometry, just be careful. There's one thing to look at when we go to apply it, is that we have positive and negative pressures on our building. They're negative, negative, and we have negative internal. Negative is away from sheeting or cladding or whatever it is. So if you're on the outside, negative is out, and if you are inside, it's there. So that's negative and that's negative. They actually act in opposite directions. They counteract each other because you do it from the perspective of where you are. A negative internal pressure is a suction pressure, it pulls in. A negative pressure on the outside pulls out. They oppose each other. So that's why you have when you are calculating your values, CPE minus your CPI. And that accounts for the fact that they act in opposition to each other. Positive is into it, so positive, 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 and then well, let's just use another color, just so we're careful. Positive, 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 and then you've got to be very careful with your sign convention, just to make sure you haven't made any mistakes with that. A final thing to consider is that we've been talking about heights in terms of where do we consider the height. And when you're looking at a building, you want to be able to apply wind pressures to it. And depending on where you are in the building, you'll need to use different heights. If you are on the windward face, you will have a height of the wall. The windward face would be, for instance, this would be a portal frame building. We would use the front face. And so you can, let's say, call that ZD. You'll see in subsequent videos, the front face is zone D, where all the other ones, you would use Z, A, B, C, and E. All your other zones, you would use the height of the building, where ZD that's your windward face, that's where the wind hits, and you'd use the height of that wall. Now, how do I know this? All of these things are stated in the code. So if I go down, vertical walls of rectangular plan buildings, the reference height ZE for the determination of loading zones on windward walls. So that's zone D, and that's where the wind hits. Of rectangular plan buildings, walls facing the wind, depend on the aspect ratio H over B and are always the upper heights of the different parts of the wall. So look at the wall it hits, and that would be the height used. The reference heights are given in figure 7 for the following cases. And now, depending on how tall and thin your building is, you may have one zone, a uniform zone, or to become progressively more and more economical for tall, thin buildings, you have progressively less, more zones. So for most buildings, and especially in this course, we just have a uniform zone, a single pressure with a single height. There is our height of the building, the height we use to calculate pressures. But let's say now the building starts getting taller and thinner, and we don't want to actually apply that maximum pressure all the way down to keep it economic. So when we have two heights, so this is B is less than H, which is less than 2B, and you'll see the H and B dimensions are given here. And then if you have a very tall building, then you can break it up into multiple pressure zones for each part, and then there is guidance on how to do that. And you'll see you're just trying to reduce it so you don't have all of this extra wind pressure being applied, and adds on a lot of resultant horizontal force. So in most cases, to be honest, in this course we will be dealing with shorter, flatter warehouses and portal frames, etc. So this clause typically covers it, but that is what it was talking about in terms of the windward face. We have a single pressure, zone D. We have a single height, and then to the top of the wall, but then we may break it down into different zones, either one zone, two zones, or three zones. For everything else, for leeward wall and side walls, A, B, C, and E, see figure 8, the reference height shall be taken as the height of the building. Use the total height for everything else. And so now, once you have that information, you can then go on to our next session where we look at how to apply these pressures, convert a pressure of 1.2 kPa on the different sections now to the zones A, B, C, and D all the way around your building. And so one thing we have skipped, and this is just more a backtrack to tell you that this factor exists, but we're ignoring it just because we don't have time and scope in this course. But please don't ignore it in real buildings, especially on bigger buildings. When the wind blows across the building, you then have wind blowing around it. You create friction along the surface. And this friction you should design for, especially in your lateral load resisting systems. For instance, you've got roof bracing here that's holding the structure up and carrying the providing lateral stability. this friction load will have an influence on it. So you want to make sure you account for that. So as I said, we're skipping this, but just remember, because of the wind blowing across the roof, you do get friction. You should account for that, but yes, we are ignoring it. But you would normally apply it over a specific zone, get the friction force, and add that onto your bracing system and make sure your bracing system can accommodate that. Okay, so that's taken us through this session where we've gone from how do we take our building and find a pressure acting in the area of it, depending on where it's built in the country, how high above sea level it is, and accounting for terrain roughness and those sorts of factors. Okay, hope that helped.